In my initial analysis, I had attempted to use rifle muzzle reports to identify shot locations. This seemed like a good simplified approach to use because muzzle reports always travel at the speed of sound from the location of the shot, whereas supersonic cracks emanate from the bullet itself and require more complex calculations to process correctly. In the end, however, my simplified approach turned out to be naive. This dataset has demonstrated to me that any sound recorder within 50 yards of the path of a bullet will record the bullet's sonic crack, and that crack will arrive a significant amount of time before the muzzle report from the rifle does. For shots 1 through 8, most of the sound sources I used for my analysis were so close to the shooter that it was impossible to hear the difference between the sonic crack and the boom of the rifle report. The one exception to this was the podium mic, which could easily differentiate them because of the distance from the shooter. For shots 9 and 10, 2 of the sound recorders close to the shooter were able to hear both the crack and the boom. However, the TMX recorder did a much better job of differentiating between the two. I'm guessing that the TMX phone was a better quality device than the DJ Stu phone. I'll play the 2 recordings of shot 10 so that you can hear the difference. Here's the good quality TMX audio, where you can actually hear a clear separation between crack and boom. And here's the Stewart video, which has the 2 sounds blended together. I realized that I would need to increase the complexity of my model to include bullet dynamics that would take into account the sonic cones of the bullets being fired for all 10 shots. A colleague was kind enough to work out the math for this and provided me with this equation. The TDOA location algorithm needs to have boom times in order to work. In other words, it's necessary to know the exact time of the muzzle report from the rifle. We are trying to locate where the rifle is, not the bullet. So that's why it was necessary for me to convert all of the crack times into boom times using this equation. I incorporated this into my model, and it made a huge difference. I now feel confident that my model does an excellent job of implementing the dynamics for all 10 shots. To implement this equation for each shot, I need to know the distance to each of the recorders as seen along the path of the bullet, and the distance from the path to the recorder. I also need to determine the velocity of the bullet at distance b. Determining the velocities was a bit of a challenge since we haven't been told what the ammunition was for any of the shots fired. Based on what I've read, I decided to use 5.56 for the first 8 shots, as well as the first counter-sniper shot, and 300 Win Mag for the final shot. For the first 8 shots, I experimented with different values and ended up with the one shown here in the circles. The Ross recorder was behind the line of fire and far enough away that no correction was needed. A bullet velocity of 2900 was close enough to work for the other 3 recorders in the vicinity of the shooter. Using 2900 in the equation, along with computing the actual distances, resulted in crack-boom differences ranging from 37 milliseconds down to 3 milliseconds. The computed crack-boom time for the cruiser was this short since it was very close to the shooter's position. For the podium microphone, I found that 2,650 feet per second resulted in the 214 millisecond crack-boom difference that was typical for what we saw when analyzing the podium audio. But those crack-boom times varied from 212 up to 221 milliseconds over the first 8 shots. Those variations could be caused by differences between the bullet paths and the microphone, as well as normal factory ammunition variations. Being offline from the podium by 2 meters results in just a 1.5 millisecond decrease in the crack boom time. So it seems like the majority of the 9 milliseconds of variation seen in the measured data was due to ammo variation. To see the 221 millisecond difference that was measured on the audio waveform for shot 1, The bullet velocity must have been 2,715 feet per second, according to the crack boom formula. That's 65 feet per second higher than the baseline velocity, which seems unusual. According to this article, cheaper factory ammunition can have a standard deviation of 20 or higher, so I guess that 65 could be a reasonable outlier for a factory batch. But there's always the possibility that the shooter's magazine had a mixture of different ammo. We just don't know. In any case, since I could actually see and hear the boom times for 6 of the first 8 shots, I used the actual boom times for those shots, instead of estimating them from the crack timing. That provided more accurate results than the crack boom estimates would have. Moving on to shot 9, I estimated that would be a 110-yard shot from the grass area north of the bleachers, and I came up with a 2,800 feet per second velocity estimate. For shot 10, I estimated 300 Win Mag from the south barn and came up with the velocities shown here based on this manufacturer's chart. Again, we don't know what actual ammunition was used, but this chart seemed to be a good starting point, and the numbers actually worked out quite well. Okay, so I plugged all of these numbers into my updated model, and let's take a look at the results. I'm going to show you 4 sets of results, each determined using different sets of recorders. The first set uses Ross, the police cruiser, and the podium. That makes a nice large triangle, which is going to give us the best TDOA results because any small errors in recorder position or timing won't be amplified as much. Then we'll move to a smaller triangle with set 2, Ross, DJ Stu, and the podium. Then a smaller one with Ross, TMX, and the podium. Finally, we'll even try the small triangle formed by TMX, DJ Stu, and the podium. This very narrow triangle is going to amplify any small errors by quite a bit. Here's the first set using Ross, Cruiser, and podium. Let's zoom in here. All 8 shots fit in a very tight group, with a radius of less than 4 feet. This group is going to be the best because the recording sources are spread out the most and they are stationary. Moving on to the next group with Ross, Stewart, and the podium, the results open up a bit, and we see a spread of about 13 feet. Looking at Ross, TMX, and the podium, we've spread out a bit more, but it's still not bad. It's a 20-foot spread. But when we zoom out and see the size of the roof compared to the spread, it's really not bad. And here's the data from the smallest triangle. It has a spread of about 27 feet. Of course, look how great the stationary data set looks at this zoom level. Now, let's go take a look at shots 9 and 10. Shot 9 resolves to the grassy area where we now know the Butler ESU officer took the shot that possibly hit the shooter's rifle and caused him to stop shooting. At least that's one explanation that's been reported. Here are some images from Dave Stewart's video that was taken just a few minutes before shot 1. You can see several ESU members near the flag crane and a close-up of this guy. He looks like he's really keeping an eye on what's going on over near the AGR building, probably scanning the dozens of people gathered along the fence line over there. Now here's a body cam image that shows the ESU officer about 10 seconds after he took that 9th shot. Zooming in, the image gets pretty grainy, but you can see that he's standing about on line with these 2 trees here and the corner of the building. We can't see the shooter in this image, so could the ESU officer see the shooter on the roof? Well, if I have him positioned correctly here, which I believe I do, it looks like he did have a clear line of sight to the shooter, which certainly makes sense. When I bring up the other 3 results, you can see they are fairly close. There's a 14-foot spread between these 2 groups. It looks like this line of sight is just to the left of the tree as well. Now, looking at shot 10, we see that it does indeed come from the south barn. The reason I did not get the correct location for shot 10 in my previous analysis has to do with the fact that it's outside of the TDOA triangle, coupled with the fact that I was not properly determining the crack boom times for the 5 recorders. Let me show you the TDOA curves for the last few shots. Here we are showing TDOA hyperbolas for all of these recorder pairs, covering all 5 recording sources. Here you can see that they all cross over nicely at the shooter's position. We get an excellent answer for shot 9 because it's located close to the middle of the TDOA triangle. So that makes the curves intersect at large angles, making the intersection point clear. On shot 10, since the shot comes from outside the triangle, the curves are intersecting at shallow angles to each other, and that magnifies any timing errors. So, for example, if the delta time of arrival between TMX and the podium was just a few milliseconds less than what it should be, the blue curve will have a flatter slope, and the intersection point will quickly move northward. With these curves all lining up as well as they do, I now have a very high level of confidence that I've got all 10 shots modeled correctly. But we are still going to have some people insisting that some of the first 8 shots did not come from this location on the roof. One of the proposed alternate locations is a wall vent located here. So let's see what happens when I set the ground truth to be this location. We do get a solution, but it's incomplete. See that shots 1 and 2 did not resolve out of the TDOA equations? I think that's because DJ Stu was running during the first 3 shots, and that makes it more difficult to force a fit to this location and have it make sense. If I use the data from the stationary cruiser instead, all 8 shots display properly at the location I forced them to. But now, let's look down at shots 9 and 10. How did they turn out? Shot 9 is close to this utility pole, which does not align with the police body cam video. And shot 10 is nowhere to be found. That's because it didn't resolve to a location. If I use the data from Dave Stewart instead of the cruiser, it puts shot 9 over here by the barn. And like before, we don't get a solution for shot 10. Let's look at the TDOA curves to see why this happened. The curves look fine for shot 8 using the wall vent as ground truth. But looking at the curves for shot 9, we see a problem. There are 5 possible answers for where the curves intersect. So we get different answers depending on which of the sound recorders we decide to pair up to form the TDOA triangle. And moving on to shot 10, we see another problem. The red and blue curves did not plot at all. This indicates that there was no solution for the TDOA hyperbolas for these data pairs. So forcing the data to the wall vent really messed up the results for shot 10. For the 4 curves that did have a solution, we do get 3 random intersections here along the middle, but there is clearly no single point that all the curves resolve to. So, back to the 4 data interpretations that actually make sense. We know where the shooter was, and we know where the 2 shots came from that took out the shooter. Some reports have indicated that the final shot came from the Washington County SWAT team that was positioned down here in the covered bleachers next to the tractor pull area. While it's true that there were some officers stationed here during the rally, my data set clearly determines that none of the shots came from that far south. I can now say with confidence that shot 10 came from here. And one of these 2 guys on top of the south barn took the final shot. The results I presented here show an overhead 2-dimensional view of the data, but all of the computation was actually done in 3D. However, the fact that the 5 audio recording sources had very little elevation separation between them meant that accuracy on the z-axis was limited. Even so, the elevation results that were generated all seem reasonable. This chart shows the coordinates and the elevation results generated by the algorithm. They may not be perfect, but the results all look reasonable to me. And finally, here's what the 3D data looks like in Google Earth. So, to wrap things up here, I've been able to successfully identify the exact locations of all 10 shots, and I've reinforced the correctness of these results by showing that all 5 of the recording devices report consistent answers, no matter how they are paired up. It was a huge challenge to time-align multiple recorders that were not synchronized to begin with, and I'm glad I was finally able to get everything squared away with my model. I've certainly learned a lot throughout this multi-week project, and I really appreciate all of the helpful comments and suggestions that I received both here on YouTube and in other forums. If you have any questions or comments on this video, please feel free to ask. Thanks for watching.